So this presentation is about nearest neighbor classification, and this is one of the most simplest yet powerful machine learning algorithms. This is often referred to as the k-nearest neighbor, and this algorithm is widely used because of its intuitive approach and effectiveness in solving real world problems. Through this session, we'll explore how the algorithm works, why the idea of you are who your neighbors are is its core philosophy, the importance of choosing the right number of neighbors, and how different distance metrics can impact results. We'll also take a look at some interesting applications in domains like fruit classification and social sciences. Okay, so let's start with our presentation. So, what is nearest neighbor classification? Nearest neighbor classification is a supervised learning algorithm that is primarily used for classification tasks. In simple terms, it predicts the class of a new data point by looking at the classes of nearby data points from training dataset. Imagine you're trying to identify an unknown object and all you have is a set of known labeled examples. You compare the unknown item to the known ones and pick the label that's most common among its closest matches. This algorithm doesn't assume anything about the data beforehand. It's entirely data driven, which makes it non parametric and very easy to understand and implement. So we have these 3 points. It's instance based learning, majority vote principle, and non-parametric approach. Now coming to the concept and the intuition of what is you are who your neighbors are. This phrase perfectly captures how the algorithm works. Let's say you're trying to classify an unknown fruit. If its three nearest neighbors in your dataset are apples, it's more likely an apple. In human terms, if a human lives in a community where everyone shares similar behaviors, features, it's likely that this person shares them too. Nearest neighbor leverages this natural pattern recognition by comparing new points with their closest surrounding data points and assuming similarity based on proximity. Now, we'll talk about how the algorithm works step by step. The nearest neighbor algorithm follows a simple but structured four-step approach. So the first approach is we'll choose the value of k. That is, we'll be determining the value of k by selecting the number of nearest neighbors to consider for the classification. And now second step will be calculating the distance. So for each data point, we'll measure the distance and then we'll get a new data point and every point in the training data set. And based on these computing stuff, we use a distance formula for calculating these distances. And for the step 3, we identify the neighbors. And how do we identify neighbors? We sort the distances and pick the top closest points. Next, we assign a class. How do we assign classes? Look at the labels of these neighbors. Whichever class appears the most is assigned to the new point. That is the most frequently, most highly interpretable one. That is how the class is assigned. Now coming to the fifth slide, which is choosing the optimal value of k, and this is a very important point. For selecting the right value of k, we choose the right value of k in a crucial way because it directly influences the performance of the algorithm. A small k makes the model highly sensitive to noise. Just one outlier could lead to incorrect classification. A very large k, on the other hand, might dilute the influence of relevant neighbors by including too much distant, irrelevant points, which can lead to underfitting. Ideally, k is chosen through trial and error or using cross validation, where we test multiple values of k and choose the one that gives the best accuracy. Also, using an odd value of k helps avoid ties when dealing with binary classification problems. So, selecting the right k is really crucial if we take a small k, it will lead to overfitting, and if we take a large k, it will lead to underfitting. These are two terms which are very important in machine learning. And odd values of k are not at all preferred because they now the impact of distance metrics. How do the distance metrics impact? The way we calculate distance between points significantly affects how neighbors are identified. The most common distance metric is the Euclidean distance, which calculates the straight line distance between two points in space, ideal for continuous numeric features. Another metric is the Manhattan distance, which measures the distance few could only move along axes like navigating a city grid, like grid-like paths and all. So for that we use Manhattan distance. And for more flexibility we use Minkowski distance, a generalized form where we can control how much emphasis we place on the largest or smallest feature differences. And choosing the right metric depends on the nature of the data and its features. And next we have the real world applications. For the real world applications, nearest neighbor classification isn't just theoretical, okay? It's used across various industries. In fruit classification, we use features like color, texture, and weight to classify a new fruit by comparing it with known samples. For example, a fruit with red color, smooth texture, and medium weight might be classified as an apple because its nearest neighbors are apple. In social science, KNN helps researchers predict the characteristics of individuals like voting behavior or income level based on the similar individuals in the dataset. This approach allows analysts to uncover behavior patterns and social clusters in large populations without complex modeling. To wrap up, so we'll discuss a summary about all of these points. To wrap up, we can have a straightforward and powerful technique, that is the nearest neighbor classification. And the idea is that similar things exist near each other. Its strength lies in its simplicity. No heavy training, no complex assumptions. The algorithm becomes effective when we thoughtfully choose the right key, use an appropriate distance metric, and normalize data when needed. Despite being one of the oldest algorithms in machine learning, its relevance remains strong because of its ability to solve real world problems with transparency and accuracy. And this slide ends with here, and my presentation ends with this.